And we spent hundreds and hundreds of hours.
Honestly, if I was going back and picking a major as an 18-year-old, but I'd spent a couple of years playing Kerbal Space Program, I would have picked aerospace almost 100%, because it's a really cool problems that you get to solve, and the math is really cool too. And just the level of detail of planning that goes into something, like if you have to send a probe to another planet, the level of planning that goes into that, like, because it's not like you can pull over to the gas station and pick up some socks because you forgot socks, right?
Like you have to plan the trajectory at the right time, and
you got to leave at the right time. You've got to have enough fuel to get there. You've got to make the right transfers, and then like almost always what happened to me in this game is I wind up stranding somebody on Mars every time. And then you spend the entire next 2 days of your free time planning a rescue mission. Because it does a really good job of balancing the cartoony aspects. Like unless you want it to, you don't run out of like supplies. So you can crash land on Mars, but as long as your little Kerbal knot doesn't die in impact, it can just sit there. He just waits on Mars for as long as it takes for you to get back there. So it basically gives you the opportunity to plan a rescue mission like the Martian.
Then you redo that. Sounds like
there's a Kerbal Space Program 2 that came out.
It relied really heavily on the modding community, and the modding community hasn't caught up to KSP 2 yet.
Yeah.
So it's still worth going back to 1. Yeah. Yeah, and basically you can add levels of detail depending on how, like you can take their cartoony system and make it super realistic and the right distances and masses to make it up to mimic our solar system instead of a cartoon version where everything's just a little closer and smaller. Anyway, let's get back.
so.
No. Obviously, I don't mind talking about that.
So.
Plus, if you're playing that game and somebody gives you a hard time about wasting your time playing video games, you can point out that you're literally learning rocket science.
No, that's true. I remember my mom used to give me a lot of crap for playing that game. So I was like screaming around, getting excited that I was going to on Mars. And I was like, I'm learning.
Yeah, it's super cool. All right, so Zeke, we addressed your random question in exhaustive detail. Jerry, you had a question about the mechanism.
Oh yes, I was trying to find. I didn't have the Klein textbook on me that day.
Yeah.
And I was just trying to find the mechanism for it, and I was kind of confused.
So there's some disagreement about certain steps.
Okay,
That's
because
part of
I
the
was
issue.
seeing a bunch of different stuff on like what the mechanism should be.
If you look at the Klein textbook, it actually gives the mechanism for the reduction of an ester, which is actually a lot easier to understand because it's not an acid. So we kind of glossed over because the first thing that happens actually is that your acid acts as an acid. Before you can actually reduce it, you've got a strong base here. The first thing it does is it just pulls the hydrogen off to make carboxylate salt. And then it behaves like if we have more aluminum hydride around, then it does the same thing we expected before, where it attacks. But the first step is just a deprotonation and you make hydrogen gas. Second step, hydride attacks the carbonyl, and we make that tetrahedral intermediate. The other thing that mastering, this is from mastering organic chemistry, because I like the level of detail they go into. So the second step here is once you make that tetrahedral intermediate, the oxygen has to leave and we reform the carbonyl temporarily, right? So we're going to end by making the first half of this by making the aldehyde. When it's an ester, your leaving group is just the alkoxide ion, right? But in this case, you actually wind up making a pretty strong bond between the aluminum and the oxygen that's going to leave. So you actually wind up with the aluminum pulling the oxygen off. Instead of just having it leave as an OH group, which is I think what we originally discussed, that's the simple.
Yeah, that's,
Same net results, but there is a significant amount of evidence suggesting you make an aluminum oxygen bond. And that pulls the oxygen off to get to your.
see, that's what I was saying, I was like, okay, but there is a little bit of variation
Right.
between. The mechanism.
We basically skipped these two steps and said that
Yeah.
the hydride attacks here and then hydroxide leaves as the leaving group. That's just an oversimplification. That works when it's the ester. Because when not for the acid,
Right.
because when it's an ester, you don't have an acidic proton. And so if you don't have the acidic proton and you also have an oxygen carbon bond, you can't make this aluminum oxygen bond. So basically, it is a much simpler mechanism to just look at the ester. There's just and there is a lack of 100% agreement among chemists, and that you'll never actually get 100% agreement on any. It's they're the worst. But one of the things that you do, like we don't even have, I don't think 90% agreements. As to the specifics of some of these steps. So that won't show up on the test when I'm looking at mechanisms. I'd be more likely to ask you about the reduction of ester, because that very reliably. Hydride attacks the carbonyl, make a tetrahedral, then leaves. And moves on from there.
Okay.
And then from the aldehyde, then it goes through the same process we looked at.
Same process.
Sodium chloride. Hydride attacks. Makes this a minus, but now instead of making a leaving group, we just protonated it to get that alcohol. And it doesn't, we can't isolate the aldehyde going this direction. There's not really a good way to make the aldehyde by reducing an acid derivative. We can make an aldehyde, we're gonna talk about oxidation of alcohols today. We can oxidize a primary alcohol to make an aldehyde, but we can't reduce a carboxylic acid to make an aldehyde. So you have to approach it from the right direction in order to get the energy to favor things properly. In theory, we should be able to do that, but the reagents that we use commonly don't have that level of specificity. It's either not strong enough to reduce an acid derivative, or it's too strong and it reduces it all the way. There's not a, you can't get that fine line there. So if you want to make an aldehyde out of a carboxylic acid derivative, is you reduce it all the way to the alcohol and then come backwards a step, because that on the oxidation we do have more specificity. No, it's a good question. Random questions. Why is formaldehyde such a good preservative? Mostly because it kills everything. Almost all, so it doesn't. It prevents some amount of oxidation of tissue, but mostly what it's preventing is microbes. Most decomposition is microbes breaking down tissues. So as long as you make it so nothing can grow in it, then it's preserved. And also it being a liquid also prevents some amount of the oxidation, because if it's submerged in liquid at all time, then there's no way for the oxygen to reliably get into the tissue. Over time, if you're like, you've got a sample in a jar and you repeatedly take it out to demonstrate something and put it back in, over time, that'll still break down through the oxidation. But it's a really effective preservative if you're going to seal a system and leave it. Because once all the small amount of oxygen that's in that jar reacts, no further oxidation will occur, especially if you keep it out of light. That's where formaldehyde falls apart. Is if it gets exposed to UV light, it'll actually polymerize. You wind up with longer molecules, and it winds up breaking down over time. So most stock rooms where you store stuff in formaldehyde don't have windows. Or you keep them stored away from the windows, because the light is actually probably the number one thing that will actually cause damage long term. And then they also package the formaldehyde with methanol Because as long as you keep the formaldehyde from being too concentrated, then it won't go through that polymerization as much. They actually add the methanol just to prevent polymerization. Long term, so there's been a lot of basically guess and check. Like, oh, this kills everything, we'll just store stuff in this, and they're like, oh, but it's still oxidizing, okay, well, we have to keep it sealed in this formaldehyde. Oh, but now it's polymerizing, okay, well, let's add a little bit of this. It's been an ongoing process over hundreds of years to get to the point where and obviously it's still not perfect. It's getting better, it's good enough for the most part. How often do you have a single sample that needs to be perfectly preserved that after 50 years, you can't just buy another sample if you need it? Right, usually it's 50 years is long enough that either the person who started it doesn't care about it anymore or died, or if it's worth it at that point, you just go buy another sample.
Really, like, ethanol would work, I mean, like in high concentrations, that would work pretty much related too, right?
Ethanol does work. I want to say because it evaporates too easily and it'll actually dissolve some of the tissues.
Okay.
The formaldehyde, for whatever reason, doesn't dissolve the tissues as much, doesn't break down the tissues as much, but while still killing everything. Ethanol, I think, is too close to water. And so it winds up entering into the cells and over time will break down the cells. Formaldehyde, you don't see that as much. But I'm not 100% on that, as I'm not, which is that still considered taxidermy if you're preserving something in formaldehyde? Anybody know? Taxidermy is usually just stuffing stuff, but so I don't know what you call somebody who preserves samples in formaldehyde. And we can talk about ethanol and fermentation. Ethanol is going to be really, really important for a number of reasons, not just for drinking alcohol in the future, but as we transition away from using fossil fuels as a feedstock for making plastics, where you need more and more ethanol. So it's not just drinking alcohol or even just fuel alcohol. We also need alcohol like acetylene to be able to continuously make these pharmaceuticals and stuff like that. So the demand for ethanol is going to keep going up. But as climate change gets worse and worse, then farm yields start going down. And so we have this weird situation where we need more ethanol than we ever have, but we actually want to produce less of it because most agricultural ethanol comes from corn. And we can't keep just planting and harvesting corn year after year after year. It's terrible for the soil, it's terrible for monoculture, for bees and ecosystem as a whole. We need to get better as a species, but especially in the US, at planting a variety of crops, which makes it harder to get the same products out at the same yields. The reason that corn is grown the way it is because it's really, really good at obtaining ethanol and beef feed from corn. Really, really effectively. If we switch away from corn, our yields are going to go down. It'll be healthier long term for the ecosystem and for the planet, but in the short term, that's going to cause market inefficiencies and lots of problems. Which, not to get too political or economic about it, but that's one of the biggest problems with capitalism when it comes to climate change. Is that capitalism inherently is not capable of taking the hit. You want for a couple of years to switch over to something that's better long term. That's not the way modern capitalism works. So in order to, that's not, but it's especially in a modern, like you used to be, not you used to, but like you used to see things like that where a CEO of a company, the owner of a large company, would make a financially devastating decision that was better long term. Like railroad barons used to do stuff like that all the time. They'd see a ton of money in something that was not going to make them money for a decade, but then eventually would have positive results. But the reason I specifically call it modern capitalism is because of the emphasis on quarterly returns in the stock market, and being publicly traded means that if you don't get results in 2 quarters, you're off.
Yeah.
Everybody's pissed off. And so it's just not, we're not in a system right now set up to be able to make good long-term decisions about climate and agriculture. So I think there is a chance that the ethanol prices will go up. It's almost certain. Hopefully, if ethanol, if we get to the point where ethanol is completely exhausted because agriculture has gone so badly, I think we have larger problems like mass famine and breakdown of modern society. So I don't think as many people will be as worried about methanol or ethanol production at that point and feedstocks and all that. But hopefully I'm just being pessimistic. That would be, it would be a great thing if you could have a system of government or economics where there was a central governing body that was able to make the unpopular decisions. In a way that was better long-term for the environment. But now we get into the political side and the international diplomacy side where those sort of economies tend to get trampled on. So you just have to go back and look at US interventions in the 60s and 70s during the Cold War to see what happens if you have a blossoming communist or socialist republic that is a threat to capitalistic society. Capitalistic society doesn't want that. Yeah, go back and look at COINTELPRO. Read some Wikipedia articles about the CIA and the FBI interventions in the 60s, 70s, and 80s for an idea of what happens when any socialistic republic starts looking too promising. Anyway, that's enough of my rambling. Y'all are getting really good at asking the right questions to keep me talking for 20 minutes. But it is, yeah, there are a lot of science professors, especially that will say like, well, why would you ever talk about that? You just talk about the science and you ignore everything else. But I find it difficult to separate the science issues from the larger, exactly. And I think I would be doing you a disservice to not at least point that out. I don't expect everybody to agree with me on political stuff, but to at least point out the connections, I think is important. All right, so let's review by doing the green yard. Let's try drawing out your mechanism for this. Get some mechanism practice. I would say the on the test, one of the things you want to make sure that you do is that when you're drawing arrows, we're always showing electrons moving. So the arrows should always originate at a bond or a lone pair. It's a little nitpicky, but even if I'm showing the lone pair on this carbonyl attacking or getting a proton transfer from something else, don't just draw it like that. Draw the lone pair so that you get yourself in the habit of making sure that you're starting out electrons. And they're always moving toward the nucleus. And a lot of times in the green yard reactions, they won't even write the magnesium and the bromide out when they're drawing the mechanism, and that's fine too. If you just drew this as the carbanion, I would consider that a full credit answer too. It's because that really does behave like it's the carbanion. Like if there's a low, Where what this doesn't capture is that you won't see any rearrangement. Carbanions have the exact opposite rules of stability of carbocations, which makes sense, are opposite charge. But you won't see any rearrangement of the Grignard reagents, which is one of the reasons why I think it's more effective to show it like this. Because it makes the point that wherever the magnesium is attached is where you're going to attach it to your new molecule. So then that gives us an intermediate that looks like. Oxygen with a negative charge, we added a methyl group. And then we just have a proton transfer, right? To get our final product. So with the exception of lithium aluminum hydride with an acid, our reductions are actually pretty straightforward reactions. You've got something with a negative charge, either a hydride or a carbon with a negative charge that attacks the carbonyl carbon. And then either a leaving group leaves or we just have a proton transfer. Second one, first step, your Grignard reagent attacks carbonyl. You make a tetrahedral intermediate. You get an intermediate right off the bat that's gonna move like this, right? What's the next step? Reform the carbonyl, and how do we do that?
The lone pair to the negative oxygen goes down, makes a double bond, and then the bond attached to that goes across.
Yeah, and your leaving group leaves. Okay. So, and I think I've said this before, but I'll reiterate, I find it really helpful with these ring opening reactions to make sure that I don't lose a carbon anywhere. To try and draw all the carbons in the same spot. That makes it a little bit easier to see what's going on here. So this was our CH3 that we added. There was the oxygen that was attached. Otherwise, I find it really easy to just wind up dropping a carbon completely. And then once you get here, now you can unfold it because you can count how many carbons in a row it is, right? And so it might be an advantage to just rewriting it. So this is 1, 2, 3, 4, 5, 6 carbons. And you have carbonyl on carbon 2. And we have an alkoxide ion on carbon 6. Maybe it's just my mind, but I have trouble jumping from this to that without trying to draw them all in the same general spatial orientation first. And then what's the next step? Not yet, we're still under basic conditions, right? So eventually we're gonna do that, but we'll have 2 proton transfers that we need to do at the end to get the 2 alcohols, so we'll just do them at the same time. I probably wouldn't mark you down if you did your proton transfer now, but we don't really have any water around, so the hydrogen drawing something to have that
It's in
proton
separate
get up.
steps.
Exactly. It makes a little bit more sense to do your second, your next methyl addition, yeah. And now we do 2 proton transfers. And again, you don't need to show them as distinct steps. If you get to here and then just did. Draw your 2 H2O molecules. Typically, we don't do that, but when it's the same step and it's something as simple as a proton transfer, I'm okay with you step showing both proton transfers at the same time. Final product. And despite how complicated both the starting material and the final product are, there's no stereo centers. Because that carbon has 2 identical methyls attached, this carbon has 2 hydrogens attached, all of the other carbons have more than or 2 or more hydrogens attached, so. Don't need to worry about stereochemistry. If we're starting from a planar molecule, are we really ever going to get a preference when it comes to stereochemistry? Maybe if we were talking about a bicyclic, something that had some large amount of stereochemistry to start, you might be able to say that prefers one versus the other, but for the most part, if you're starting with something planar and we're doing an addition to it, it's going to add from both sides mostly equally. So more writing for that one, but mainly just because one, we had to show a ring opening reaction, and it always pays off to be careful with that. And then 2, because we had to do the Grignard reaction twice. There are a few things about the test I was going to bring up in the reactions and mechanisms. Oh, just while we're on the topic of mechanisms here, this is a little nitpicky, but when we do a ring opening reaction, so first off, it was under acidic conditions, so our actual intermediate, so this was on the first mechanism, so page 7. So the intermediate that'll actually go through the ring opening reaction, you had to protonate it first before you did the ring opening reaction, because we're under acidic conditions. Then the other point that you always want to see, so one, it's going to be backside attack, where we wind up with our nucleophile approaching from the opposite side. But which of these two carbons is it going to attack? Or eat both equally?
I know the answer for substitute rule, but I don't remember why.
So anytime we have these three-sided ring structures, there was that term that we briefly used, the Hammond postulate. The Hammond postulate was that when you have a strained structure like this, the bond that is weaker is the one that is gonna be on the more substituted side. That's a little bit glossing over the Hammond postulate. The Hammond postulate was actually that your intermediate, if your intermediate is closer to the energy of the activation energy, then it looks spatially more like the transition state. Basically, what it winds up being is that you wind up breaking this bond on the more substituted carbon, even though we would normally say SN2 doesn't go for tertiary. But because these two bonds are not equal, this bond is actually weaker. It's more stretched already, so it's lower dissociation energy. So even though there's some more sterics, but that's really nitpicking. I just wanted to remind, there are a few mechanisms where we have this three-sided ring structure, we do a ring opening reaction. You're always gonna do the bond that breaks in a ring opening reaction is the one that's on the more substituted carbon.
I was looking at that like the day before and it clearly did not do that, so, well, that happens.
It happens. It's one of those things where once you get out of the test taking environment, a lot of stuff.
No,
comes
literally, I
flooding back.
literally went to the library and I was like. Stuff I missed.
We'll do, if anybody has more questions about the test in particular, I'll give you, you can take a look at it during break. And after break, we can spend time going through any more of the problems, the reactions or mechanisms, if you don't know what you missed or why something happens. But we already did the synthesis problem and we went through the first 6 or the first 4 pages already the other day as well. So mostly the mechanisms of the reactions. If you have questions, we can go over that after break. All right. So we won't draw the mechanism for both of these. But the products are pretty straightforward to draw. In both cases, reduce to an alcohol or to the alkoxide, and then the second step is just the proton transfer. So we're going to make an alcohol in both cases. So for A, we're going to get both the R and the S in equal amounts. There's no weird sterics going on here, so there's almost exactly a 50-50 chance of adding the hydride from below or above. And the sodium borohydride, is that going to affect the alkene?
No, it's not strong enough.
It's not strong enough to. And for the most part, when we hydrogenate an alkene, it's going to be with, hydrogen gas and a solid catalyst. So we'll wind up reducing the carbonyl, but leaving the alkene alone. Is there anything significant about the second step having methanol instead of water? What was the second step? Just a proton transfer. So any protic solvent works for the second step. We have to be careful with it when it's lithium aluminum hydride in particular because it's so reactive. Needs to be 2 steps. Technically, this could actually be 1 step. But maybe it's separated as 2 steps because maybe methanol is a little more reactive with the sodium borohydride. than water is, but I doubt it. I bet you could write that as one step just fine. Alright, so reductions aren't too bad, which is good because oxidations are a real headache, and that's where we're going next.
Wait, real quick, what's the reduction, I mean, if we were to use lithium aluminum hydride, that affect the double bond? That one?
I would need to go back and double check. I don't think so though. In general, if you're gonna hydrogenate double bond, it's gonna be hydrogen gas. Over break, or remind me when we go to break and I'll check the slides, because I think I had a slide on that on from Tuesday.
Okay.
All right, so. The text you can't really read says, if carbonyls can be reduced to produce alcohols, what inverse reaction can we expect? Carbonyls reduced to make alcohols, so alcohols can be oxidized to make carbonyls. And there's there's 4 flavors of oxidation. That we're gonna talk about. There's the simple efficient version, which is just basically you can oxidize it with chromic acid. If you have dichromate under acidic conditions, or you can actually just write it as H2CrO4, so that's chromic acid. Chromic acid is not particularly stable, and it's also really toxic in addition to being really acidic. So we don't actually generally use chromic acid directly. We make the chromic acid in situ. Is the Latin for in the process or in the situation. Basically what that means is if you take dichromate and you put it with a strong acid, you make chromic acid. So rather than keeping it in the stock room as chromic acid, because it's so nasty to deal with, we keep it as a solid. And then sulfuric acid is really common. Everybody has sulfuric acid and it's cheap and easy to store. So if you take a primary alcohol and you expose it to either chromic acid or this combination of reagents, sodium dichromate, sulfuric acid, and water, will oxidize to make carboxylic acid. Or if it's a secondary alcohol, when we oxidize it, we get a ketone. We can't further oxidize a ketone without breaking a carbon off. So basically it'll stop here. So this is actually one of the, and then what would we expect from a tertiary alcohol? Tertiary alcohol, you can't break a bond, a carbon bond. So basically tertiary alcohol won't react. So this is actually one of the easiest tests to determine what type of, if you are given a random white powder and you're told to figure out what it is, you take an IR of it and you figure out it's an alcohol, or you smell it and you think it's an alcohol. If you don't know what type of alcohol, is it primary, secondary, tertiary, or a phenol? One of the easiest tests is to expose it to chromic acid. Because if it's a primary alcohol and you expose it to chromic acid, you get a carboxylic acid out, which shows up really obviously in an IR. If it's a secondary alcohol, you get a ketone, which shows up really obviously in an IR as well, right? You'll get the carbonyl peak around 1600, but without the giant peak of at 3000. And if it's a tertiary alcohol and you expose it to chromate, you're going to get no reaction. And when you take an IR, it'll look just like the IR you had of the first material. And then the last class of alcohols is what? Primary, secondary, tertiary, and phenols. Phenols actually make a weird complex with chromate that's actually like this really deep purple blue color. So you can actually just tell visually, if you add chromate to do this test and it turns dark blue, it's a phenol. It's not either of the other, any of the others. That's something that comes up most often in that upper division class I took on organic qualitative analysis, where your final is here's the white powder. One of the first things you did if you thought you had an alcohol was get some chromic acid and see what happens. The mechanism for this isn't too bad either. Basically, if you have chromic acid, first thing it does is it makes what's called a chromate ester. And that one we don't even usually show the steps for, because when we have these inorganic compounds, they tend to react in unfamiliar ways. Once you make the chromate ester though, if there's water around, it'll just go through an E2. Water will actually act as the base. Water is a strong enough base to go through an E2 reaction for a chromate ester. And what winds up happening is your water pulls the hydrogen off from your alcohol carbon, and the chromate leaves and takes the electrons with it. And in doing so, those electrons from the carbon hydrogen bond move over to make the carbonyl. So we actually wind up reducing the chromate. It's no longer chromate. This chromate is CrO4 with a -2 charge. We actually make a chromite, or hydrogen chromite, technically, if you remember your rules with polyatomic ion names. Good, that means that the closed book quizzes worked. If you take away an oxygen, but it has the same overall charge, then it goes from an 8 to an 9, right? So we actually wind up reducing the chromium, the chromates, to make chromite. Will be hyperchromite. Which I don't actually think chromium will do very well. I think it'll jump all the way to a chromium as being neutral. They skip that oxidation state, if I remember it correctly, but it's beside the point. However, this still has a similar problem to what we had before with lithium aluminum hydride, in that you can't stop at an aldehyde. It'll take the alcohol and take it all the way to carboxylic acid, but it's really difficult in low yield to try and make the aldehyde from this reaction. So we actually need a different reaction if we want it to stop at the aldehyde. It's still a chromium-based reaction though. So if you want it to stop, then you actually use this reagent called pyridinium chlorochromate, which is actually going to start with the chromium in that more reduced state with a chlorine attached to it. And so this just gets abbreviated as PCC. We have to do this in an aprotic solvent because we have some acid-based things happening here, and so we can wind up with aprotic solvents and throw a wrench in the works. So if you have PCC, it's a more expensive reagent, and it also has lower what's called atom efficiency. Basically, the bigger your reagents are, to accomplish the same reaction, the less efficient it is, because in general, this is gonna be a much more expensive molecule to buy. And usually ship, because they tend to also have high molecular weights, right? Which means you get the same number of moles, you have to pay to ship more grams. So for your sodium dichromate, it might be $50 for 100 grams of it. But 100 grams is, enough for 50 reactions. 100 grams of the PCC might only be enough for 10 reactions, because it's 5 times the size in terms of molecular weight. So that idea is called atom efficiency. And when you're thinking about synthesis problems, that is something that synthetic chemists are thinking about all the time. It's not just the yields. They also have to be thinking about atom efficiency. Yields, depending on, and it really is it's a cost benefit analysis, really. Sometimes atom efficiency matters more. You're willing to take a lower efficiency reaction if it has better atom efficiency, depending on the actual cost and what you're trying to make and how much you can sell your product for. There are some times where atom efficiency doesn't matter at all, because you're either you might be making something that's so valuable that getting the yield matters more than having the atom efficiency. But it is more, it is sort of an economic concern when you're planning out these syntheses.
Fair to say that for the most atom efficiency.
Yes, but it has other practical concerns, right? It's a gas. So all of these things are things that you have to keep in mind when we're planning this stuff out. But yeah, just from sheerly how the molecular weight per mole is lowest, so it is going to have the highest atom efficiency.
Expensive, it's not the cheapest thing, but.
It's not the cheapest thing, and it's hard to store.
Yeah.
You have to keep a hydrogen tank around all the time, or you have to generate it in real time. Which is not uncommon with hydrogen, because nobody wants to store tanks of hydrogen if you don't need to. So if you need to use hydrogen, sometimes what you'll do is you'll just react aluminum metal and hydrochloric acid will give you hydrogen gas, not at high pressures. But if you just need a source of hydrogen gas, you can make it, you can generate it yourself from really cheap stuff. But that's an extra step when trying to design a process for an industrial factory. It might be, there's a crossover where it becomes worth it to just have a tank of hydrogen.
Cost benefit.
Exactly. All right, so the problem with these two, we won't go over the next two mechanisms yet. But I want to talk about why we can't just stick to PCC and chromic acid. Those accomplish everything we want out of oxidation. The problem is chromium, really nasty. Is everybody familiar with Aaron Brockovich?
Yes.
So it's a story about a town, PG&E town down in, is it Barstow? Somewhere in the desert, somewhere between Bakersfield and Las Vegas. There was a small town that was just a company town for PG&E. PG&E was storing some of their waste, which was chromium ions as chromates for the most part, in this pool that was lined with plastic. But that plastic had leaks in it, and so the chromium was getting into the groundwater. And so for about a decade, this town had horrific birth defects and like astronomical cancer rates, like 50% cancer rate by the time you're 30. And it wasn't, and they basically just kept burying evidence of it. Aaron Brockovich was a paralegal from that town who went and gathered all the evidence on her own. Julia Roberts made a movie about it, I think in the 90s probably. But it's a good watch because it actually it informs a lot of how government policy regarding PG&E in California was as a result of the Aaron Brockovich case. So obviously chromium's a problem. It's a problem to store, it's a problem to get rid of, it's really toxic if you're working in a lab that's using chromium all the time, that's less than ideal as well. So in the interest of green chemistry and trying to promote other reactions that accomplish the same thing without using really nasty reagents, we have a couple other options. Neither of them is perfect though. From point of view of us looking at it on paper and getting good yields, chromium actually works the best. But we're trying to phase it out. With things like the Swern oxidation. So we're gonna come back over these in a second, but I just want to look, the two other options, the Swern oxidation. And the Des-Martin periodine oxidation. Both accomplish the same thing, where you can take alcohol and turn it into an aldehyde or a ketone. But they both have their own individual drawbacks. In the case of the Swern oxidation, you actually wind up making dimethyl sulfide, which is really nasty smelling. Smell rotten eggs, basically. You generate it in really high concentrated amounts in the process of this. And the periodinane oxidation, neither of them has as good an atom efficiency as PCC or chromic acid. So they're both more expensive. Neither one of them will give you as good a yields as these two, but they avoid using chromium. So basically, if I had to guess in 20 years, I doubt that these are even taught except as historical notes. Because everything's moving this way towards, it's okay to have lower efficiencies if you're doing it in a more safe and sustainable way. As long as we get capitalism out of the picture, right? Yeah. All right, let's take a break. We'll look at these mechanisms at 5 after.
Gonna remind you about.
Yes, thank you. Let me look at, it was your question was on the.
That full effect of double bond.
Oh, right. Yeah, thank you. I don't think hydrogen, lithium aluminum hydride will react with a lot of stuff, but it still needs a partial positive to attack.
You're gonna find out.
Hey,
They booked a hiring committee meeting right in the middle of my lab Thursday.
the afternoon one or the morning one?
Morning.
Morning. The lab, right.
So I was thinking about just switching the ICA and the wet lab next week.
If that'll work, that works too, or otherwise it's an excused absence for to be on the hiring committee, so we can get a sub without taking sick leave or anything too, if Marika is available on Tuesdays or Thursdays. Or Raina. But if it's easier than organizing that, if it's to just switch the ICA in the lab that week, just do that, that's fine.
So,
Then we're recording,
oh,
just so you're aware. I would go this way anyway.
So I will, I think actually.
I closed it on, their apps close on Monday, and then we have to screen them by the following Monday, and there's already 31 apps in there. So,
It's like grading, how do you do that without getting like fatigued and, you know, like how do you?
right, that's, we gotta use this weekend so that we have next weekend to do all the ones that are gonna come in on Monday.
Alright, that's great.
All right,
Are you gonna be? Or observation?
no, we'll talk about it, it's unlikely that I'll ask you about it, because it's a really kind of nasty one. And involves both sulfur and chlorine in non-standard uses. So we'll talk about it. But for the most part, for all of the oxidation ones for oxygen, the main thing is gonna be knowing that is the synthesis applications. Not gonna forget my coffee cup here today. And the first top half, of this is just the reactants reacting with themselves to make this chlorodimethyl ion, which then reacts with the alcohol.
Yes.
Yeah, so like I said, we'll talk about it, but it's,
Did you bring your other thing? Reaction time, it's like,
yeah, not.
we're not. Gonna do that, it's not right, that was.
Yeah, and I believe this is one where they're still figuring out the mechanism. Because I think both of these, swarm oxidation might have gotten mentioned in my upper division OChem class. But neither of them was in my first year OChem. Class, just because
Just came up with.
it was green chemistry was still in its infancy. In the early 2000s, we were aware of things like sustainability,
Right.
but they weren't nearly as big of a push. Chemists generally think they're exempt because we don't make things at super large amounts.
Yeah, it's almost like conspiracy.
There was still that going on as well, yeah. Sorry. basically, it's just like saying, like the rest of the molecule, this is just showing you that OAC means that it's an acetate group.
Why not just R?
Good question.
I'm just.
Yeah, they're just defining their variables there, that's all. All right. So before we dig in here, did anybody have any questions about mechanisms or reactions?
Looking through and think I know what I did well.
Yeah, I think in general, when you sit down with your notes, I think most people will see what they missed in any of those reactions. I think probably the biggest one was mixing up Markovnikov and anti-Markovnikov on, it's easy to do. On the testing situation in particular. Anyway, so let's talk some more about Swern oxidation and the DMP reaction. So one of the things that's also worth noting is Swern oxidation, you have to do it at really low temperatures, -78 Celsius, which that seems like a oddly specific number. That's because that's the boiling point or the sublimation point of dry ice. So basically you need a dry ice bath for this to work. And you can't just use water like we would for a normal ice bath because they'll freeze if you do that. So what you have to do to get a cold bath at -78 Celsius is you have to use a different solvent, something that won't freeze at -78 Celsius. Which typically either ethylene glycol, antifreeze, also freezes right around that temperature, but the other one that actually works better usually is acetone. Acetone freezes at about -90 Celsius. So if you do an acetone and dry ice bath, you can actually keep something at -78 Celsius with a pretty high degree of specificity, just like an ice bath will keep something at 0 Celsius. And the Swern oxidation does have some advantages in that it is specific, like PCC, and it'll stop at an aldehyde. It makes DMS dimethyl sulfide, which is nasty smelling and pain, but it also is volatile, so it's easy to remove from the reaction mixture. So Swern oxidation is probably the most is the best option to replace number 2 at least. The problem is the mechanism is not fully understood and it's nasty. The whole first step, the whole first half of this is actually the DMSO reacting with oxalo oil chloride. That molecule, let me go back for a second again. The COCl2 is the acid chloride version of oxalic acid. So I believe it's called oxaloyl chloride, which solid slil. I think I spelled that right. It doesn't look right, but that's just because it's a whole bunch of prefixes on top of prefixes and common names. So that's the COCl2. And then DMSO is dimethyl sulfoxide. So the first step is actually the DMSO reacting with the oxaloyl chloride. Yeah, there it is. It didn't spell it right. Oxaloyl chloride. To make this chlorodimethyl sulfonium ion. and it's not terrible as a mechanism. We wind up making carbon monoxide and CO2. So again, things to keep in mind in terms of ventilation. But the main thing is that this chlorodimethyl ion winds up actually being the reducing agents. You actually have the alcohol oxygen act as a nucleophile to attach to the sulfur, and then a proton, and then you kick off the chlorine in order to do that. Then we have the triethylamine acts as a base. Triethylamine acts as a base again, pulls off and goes through it's similar to a elimination reaction, actually keep a negative charge of carbon in that case. Like I said, this is a nasty one, and it's not particularly relevant, and the reason that I'm not gonna spend a ton of time on this or test you on this is because whether or not this is actually the active molecule reducing agent is still up for debate. So I'm not gonna make you learn something that's not fully understood at this point anyway, especially when it's this complicated for no good reason. There's no learning benefit to having memorized this compared to some of our other mechanisms, right? So I want you to be aware of it. But this mechanism in particular won't show up on a test. The Des-Martin pyridinane oxidation is even worse in terms of additive efficiency, especially because iodine is such a high molecular weight. And it's a really big, this DMP molecule is a really tricky one to work with. It's a large molecule, but the other thing is that it's shock sensitive. Which means that it will explode if you drop it. Less than ideal for keeping stored in your stocking. It oxidizes things. It's a very good oxidizing agent. And again, the mechanism is not well understood at this point. I'm fairly certain that I was taught the Swerin oxidation, at least as a general, without looking at the mechanism. I don't think I ever saw this in undergrad. So this is just a new mechanism because we're trying to get away from the chromium-based mechanisms. If we're just talking about in lab or on paper, the easiest way to actually get it to oxidize and aldehyde to oxidize all the way to a carboxylic acid, to get an alcohol to oxidize all the way to carboxylic acid is still just use chromic acid. It's just not something that we want to do industrially or do too much. It does cost us more on the waste management side because it has to be treated so carefully as well. So, and just let me go, I'm gonna go back to remind ourselves, Swerin oxidation was DMSO and then oxaloyl chloride, followed by triethylamine. Those are our reagents for it. If we're trying to fill in reagents. The DMP is the name of the molecule. This type of molecule is a pyridinane. And this particular pyridinane is called the Des-Martin pyridinane after the people who first used it to do this oxidation. So DMP in dichloromethane, oxaloyl chloride, and DMSO followed by triethylamine. PCC. Or just dichromate in acidic conditions. The other place where these wind up being useful in synthetic chemistry over these, with the advantage that they have, is that they can be done with neutral pHs. These have to be in very acidic pHs, which means that there's other functional groups that can react with an acid. These first two aren't really options. Like, let's say we had an epoxide we wanted to keep as an epoxide and not have it go through a ring opening reaction. We can't expose it to strong acids because it'll go through a ring opening reaction. So these others might be options because they are more selective. And will react with the alcohol without reacting with some of the other groups. Let me shrink this down so we can see it better. And so if you've got more than one choice for the reagents, you can pick one. If they're valid. But try to use a mixture of them so that you test yourself, get some practice writing down those different variations. Yes. With the exception of aldehyde, the only restriction with these, any of those four work for any of these, with the exception of if you're trying to make an acid, it's gotta be chromic acid, so it's gotta be this first one. And if you're trying to stop at an aldehyde, it has to be any of the other three. And even actually in the next, you're gonna start feeling old. Because all of this textbook where it says dichloromethane, that's all gonna get phased out in the next 5 years or so too.
Oh,
Because there's more research showing dichloromethane is more toxic than previously thought. And legislation to try and remove it from educational labs. And small scale labs as much as possible. So my guess is they'll have some other diprotic or aprotic solvent in place in the future for a lot of these. You're now getting to the point in your academic career where you will start to notice differences between the different editions. At the 100 level, all your textbook, your first edition versus second edition, it's not that big of a difference really, right? When you get to second, third, fourth year classes, there's still enough research going on and enough changes happening that you will notice differences. Packets. No. It's still another. The sodium borohydride would work, or lithium aluminum hydride would work. Make sure you keep it written out as two separate steps. You use the ALH. And David, I did go back and double check, and yes, our textbook in particular, but my intuition was that even lithium aluminum hydride won't hit the alkene. It matches with what we've seen before, so. All right, so 4 new reactions that all do the same thing, more or less. The one wrinkle to keep in mind out of those is that chromic acid will take it all the way to a carboxylic acid, and the other 3 won't. For a primary alcohol, they're all identical for a secondary alcohol, and none of them will react with the tertiary alcohol. So 4 new mechanisms or 4 new reactions, none of which have easy mechanisms. So let's go back to our safety blanket of SN1 and SN2. Alcohols still go through SN1 and SN2, right? Been talking about that in general terms since October. We can get these reactions, these alcohol reactions, to go backward to do an SN1 or an SN2 to make a halide. We just don't get great yields. Especially for an SN2. We can go through an SN1 if it's a tertiary alcohol, you can see an SN1 and get okay results with this, but we're still going to be limited by the fact that oxygen is the worst leaving group. The alcohols are a bad leaving group compared to the halides. So in general, especially if the alcohol is primary or secondary, we're going to go through an SN2. We basically just need to make it a better leaving group. So there's a couple ways we can do that. We either need, there's 2 approaches. We either need to make the alcohol a better leaving group, or we need to make our halide a better nucleophile. And so that's what these options do down here. We'll get much better yields than just using HBr with the alcohol. You'll get some small amount of product if you do that. Most of it's going to stay as the alcohol. if we treat it with the tosyl chloride in pyridine, followed by bromide, is this gonna make the oxygen a better leaving group or make the bromide a better nucleophile? Middle option there. Better leaving group, why?
Replace the H with TS.
Yeah, we've seen that before, but the other thing that you could look at is that all we're doing for our bromide is just throwing bromide in there. We didn't touch bromide as a nucleophile, so we have, if this is gonna work, it's because we're making the oxygen a better leaving group. This other one goes the opposite approach. Phosphorus tribromide is actually makes the bromide a better nucleophile. So it's less about the oxygen and more about the bromine in that case, and we'll look at that mechanism here in a second. And you'll notice as well, we see similar effects here. SOCl2 is another way to make the oxygen a better leaving group. Zinc chloride is another way to make the chloride a better nucleophile. Right, so we'll use the SOCl2 as an example. But this is treating the leaving group. Yeah, okay, that's what I thought. This is a similar mechanism. SOCl2 is just a smaller molecule than that tosyl chloride. So it's better for showing the mechanism here, but it's going to be really similar. The tosyl chloride was an SO2 group attached to a benzene ring, so it's just more drawn. It's the only difference, really. But in both cases, lone pair of the oxygen attacks the sulfur, which breaks a pi bond between sulfur and the oxygen. And then you kick off a chloride to reform that pi bond, just like we saw before with the esters and carboxylic acids. So now what we made is a good leaving group. We just converted that alcohol, and then it goes through a proton transfer with the pyridine in order to make this SO2Cl, which is a really good leaving group. So then the chloride can come in. Remember, we generated the chloride at the beginning, or sorry, right here. So this is one of the other reasons why this is useful, is because it's one reagent that's going to do two things. It's both the source of our nucleophile and it's going to make the oxygen a better leaving group. And it has the advantage of also making SO2 as the product, which is a gas. Anytime we can make a gas as a product, that's going to help us with our yields, right? It's going to drive our reaction more towards completion because we can remove it from the system as we go. So make a new bond to the sulfur at the expense of a sulfur oxygen pi bond. Reform the pi bond and kick off the chloride. Proton transfer from the alcohol to the base. And then chloride comes in regular SN2. This doesn't work well with tertiary alcohols though. The same reason that SN2 reactions don't really work very well with tertiary, anything tertiary, just sterics. This is a big bulky group, sulfur's a big molecule, the chlorides are big, the oxygen's not small. Bringing this up to a tertiary alcohol in order to make this new bond, there's just not enough space. So net result of this though is this is a good way to take an alcohol, turn it into a halide, which in terms of synthesis is really useful too, right? Because once it's a halide, that opens up a whole bunch of options for pretty good yields for moving that around, elimination reactions, things like that. Even making this a better leaving group, you can't get good elimination yields from it. Because you still need a stronger base to come in. And if you put it in place of a stronger base, you get side reactions happening. I had the mechanism wrong on this one. The PBr3 is another way to do the leaving group. I thought it was making bromine a better. I was thinking of iron bromide. Makes the bromine a better nucleophile. That's neither here nor there though. Really similar process. Lone pair from the oxygen makes a bond, this time to a phosphorus instead of a sulfur. If anything, this is even easier because we don't have any pi bonds to worry about. We make this whole molecule, we don't even have to do the proton transfer. The proton stays attached to the oxygen as part of the leaving group. So you just make a new pi bond, or a new sigma bond between the oxygen and the phosphorus at the expense of kicking off a bromide, and then the bromide comes back around to act as the nucleophile and kicks off the leaving group. All things considered, that's actually a pretty straightforward mechanism, right? Compared to some of the stuff we've been looking at. It's also a good time to reflect on how far we've come. If I showed you this slide in November and said that this is an example of a simple mechanism, you would have freaked out a little bit. We've come a long way since then. It's all steps that we're used to at this point, right? The big key with these reactions that we're adding is that to make the alcohol better leaving group, we're just touching that in more detail. We never touched that in detail when we talked about SN1, SN2 before. That process, though, in general, just means you're going to make a new sigma bond between the oxygen and something else. And then sometimes there's some other rearrangements happening, but then that makes it so that a regular halide can come in and act as a nucleophile and get decent yields. And again, the tosyl chloride mechanism looks identical to this one. The difference is it's a bigger molecule and it only has the one chloride instead of the two. So that means that it won't generate its own nucleophile as part of the process, which means we can control the nucleophile by adding the bromide. You could add NaCl for the second step here as well, and have, if you wanted to chlorinate it instead of brominate it. But if you're going to do that, you might as well just do this, because then it's one step. So if you're trying to brominate it specifically, which there's lots of reasons to do that when it comes to synthesis, bromines are really easy to move around. We have lots of bromine specific reactions. So if we want to bromine, these are our two good ways to do that. You can still take this approach, it's not going to be as effective though. And neither of them work very well. None of these work very well with tertiary alcohols. So with tertiary alcohols, you basically are stuck, just use your acid and you're just gonna be stuck with bad yields. Or might actually be better yields if you made it a better leading group and forced it to go through an elimination. And then put a bromine on an adjacent carbon. Because we have, once we get to an alkene, we have lots of options as well, right? All right. So just practice drawing these mechanisms. I'm just gonna skip forward for a second to see what else we really wanted to. All right, so there's our elimination reactions. There's one more topic I wanted to talk about today. Before, and then next week we'll get into ethers. The ethers tend to have a lot of similar reactions to alcohols. They're not quite the same. Excuse me. Just like I was mentioning a second ago, if you've got a tertiary alcohol, if we want to get it to go through an elimination instead, because that's easier than trying to get a bad yield. Or it still gives us something we can work with. We'll lean on entropy and delta G. Right, put it under concentrated sulfuric acid. What's the concentrated sulfuric acid gonna do? It's gonna protonate the alcohol, right? Water is still not a great leading group, not as good as tosyl chloride or as a tosylate or any of those other ones we were just looking at, but it's still better than an OH group. So we can still protonate it because H2SO4 is a really small molecule. It's easy enough to get in there, even if it's tertiary, and then we just heat it. Heat favors making two separate molecules. So it's gonna favor elimination, especially since one of them is volatile. Of course, this is volatile too, so we have to be careful with that. But at the very least, we can rely on the entropy side of things to try to favor the elimination reaction. Or you can do tosyl chloride purity, make a better leading group followed by a strong base. You're not gonna, it's gonna be really slow though, because of how big this molecule is and the sterics here. So it's doable. It's still not a great option. And more frequently, you just see this because it's so much simpler anyway. And if you're gonna get mediocre yields either way, you might as well pick the one that's simple. All right, so the last topic in the last 10 minutes here is the idea of adding a protecting group. So a protecting group is the opposite of making the oxygen a better leaving group. A protecting group is going to basically cover up the oxygen so that it doesn't react. So in particular, if we wanted to do something like we wanted the bromine to react, but we don't want the OH to react. You can add a protecting group. Right, so TMS is tetramethylsilane. So if you can get TMS as a chloride, you can actually add a tetramethylsilane. Maybe that's not right. It might be TMS now that I think about it. Beside the point. It basically covers up the oxygen so that it's not as attractive. So this carbon is not as attractive as a target for a Grignard reagent or for any nucleophile. So this will basically force a nucleophile to favor reacting with the bromide and not react with the alcohol. So in this case, it's if we wanted to turn this into the bromine into a Grignard reagent. You can't just put the magnesium in with it on a molecule that also has an alcohol, because that'll actually just oxidize the magnesium. we wind up with competing oxidation reduction reactions happening. By turning it into a protective group, we make it so that the bromine can react, and then we can have the bromine react as a Grignard, or we can have this react as a Grignard reagent. And then we basically just undo it. We use the reagent TBAF. Is just going to remove the TMS. When we go back to being an alcohol. This is another case of this idea will wind up being really important if you continue on in synthetic organic chemistry. It's really common to need to find the right protective group for the right functional group. Once you get close to the end, you don't want to undo all of your hard work getting to one step from the end. So rather than trying to come up with a completely separate pathway, you just protect that one group that you're worried about reacting. And there are different protective groups for different functional groups. This TMS chloride is effective at protecting alcohols, but it's not going to be as effective at protecting other things like carboxylic acid. If you want to protect carboxylic acid, you're going to go a different route. And so the specifics of this reaction are less important than understanding the concept of what a protective group does. So this is just a summary slide. And phenol, when it reacts with the chromic acid, doesn't make a complex with chromium, it makes benzoquinone, which that makes a complex with chromium. Basically, you wind up with these pi clouds like this, positively charged metal ion floating around, and that metal ion basically sticks to the pi clouds, like iron in the middle of a hemoglobin ring. It's basically just held in place by electron clouds, and positives being attracted to negatives. If you have chromium in the presence of benzoquinone, it basically makes a benzoquinone chromium sandwich. Chromium with a benzoquinone on top and bottom, where the pi clouds are like they're almost shaped like a slice of bread.
I think coordination compound.
It is a coordination compound. Forgot you had coordination compounds back in Gen Chem. Yeah, that's what you do. It's a lot of these aromatic compounds wind up making coordination compounds with metal ions because you have these donuts of electron clouds that wind up being really attractive targets or like sticky sites where your metal ions just wind up sticking to them. All right. I think we'll end a couple minutes early since that was a lot of material. I will get your quiz going. Actually, you know what? Just to make sure, this will be your quiz this weekend. These do three mechanisms. All right, so you can work on that whenever you want, but get it uploaded, double check and get it uploaded when I get the quiz live in a couple hours.
So what mechanisms should we not worry about? Like the sworn
The
oxidation?
sworn one in particular. The other ones,
What about the DMP? That one? We're not as-
and so DMP we didn't even touch.
We didn't even-
Yeah, so. And even this one, it's basically,
I mean,
like,
the
all things
fluoridation
considered. Yeah,
chlorochromate one is kind of the same as just the chromic acid.
it's gonna be pretty similar. And basically this should be, hopefully they have this one because I can't test you on what we don't know, right?
Right, yeah.
So the first step of the oxidate for both the PCC and the chromic acid is just make a chromium ester. It's just that your chromium ester looks a lot more complicated with the PCC because you wind up with the rest of that molecule attached over here. But then the second step is just that elimination reaction. Where you wind, it's a weird elimination reaction in that you're not making an alkene, you're making a carbonyl with those electrons. The chromium pulls away and pulls the electrons with it. So the oxygen pulls electrons from the nearby carbon hydrogen bonds. So it is an elimination reaction, it just looks a little bit different than what we've seen before. And really what makes it unique is the fact that you start by making this chromate ester. So this one I might ask you about that second step. And then I'm not gonna ask you about the Swern oxidation,
Thank you.
but these ones are both fair game as well, because those are reasonable.
Substitution.
This,
even
yeah.
The elimination, I mean, the elimination ones are pretty easy.
True, yeah. But this will be your quiz for this weekend. And yeah, you should see that. That quiz will go live in